All right. So I think we're recording. We should be good to go. All right. So today we are going to start moving on from talking about how we describe functions and start talking about the different types of functions we actually look at in math class. So let's go ahead and jump into it. All right. So types of functions. Today we're going to be looking at linear functions, slopes, and rates of change. And then tomorrow we're going to be talking about nonlinear functions and a couple of other things that go along with uh, functions in general. So for now, so types of functions. As you may have guessed, or as you already know, there are many different types of functions that model real life. Things like sine functions, tangent functions, squared functions, cubic functions. I mean, there's a ton of different ones. But in general, they go into or fall into two major broad categories. And these two categories are linear and nonlinear functions. And in case it's not obvious from the name, linear functions tend to give you this straight line like over here, whereas nonlinear functions are going to give you curves and things like that. So linear functions, a linear function is a function that when graphed will appear as a straight line. That line can be either horizontal or it can be diagonal in either direction. A vertical line is not a function because remember that x value, your input there, there will only be one x value, first of all, on a vertical line, and it will have multiple different outputs. So that makes it not actually a function. Linear functions are defined by a constant rate of change. And here are visuals of the three types. This is a positive linear relationship, this is a negative linear relationship, and this is a horizontal linear relationship. So looking at the mathematical side of linear functions, if a function is linear, it will always follow the same general formula. And you've probably seen this formula before with a y instead of the f of x, but that formula is f of x equals mx plus b. This is called slope-intercept form when you write it as y equals mx plus b. You probably dealt with it in either Algebra 1 or Algebra 2, but it's good to review, and you might not have used it in as much detail as we're going to. You also might have, so we'll see. This might be peer review for you guys. M represents the slope or the rate of change, and we're going to talk more about what that actually means in a little bit. That rate of change idea is really important for real life problems. B represents the y-intercept, so that's the point that hits across the y-axis when you're on your graph. So looking first at slope, the slope in a linear function represents a rate of change. Just said that a little bit ago. We're going to go into more detail later. It tells you how much the f of x or y value changes whenever x changes. So remember, f of x and y are pretty much the same thing. They sub out for each other. But the way this works is if m equals 2, then every time that x goes up by 1, your f of x or your y is going to go up by 2, right? Because you have 2 times x plus whatever or minus whatever, it doesn't really matter. So when you have an x that goes up by 1, because of the way that formula is going to play out, your y or your f of x is going to go up by 2. If the slope of a linear function is positive, the graph of the line will go up as you move to the right. So that'll look like this. If the slope of a linear function is negative, the graph of the line will go down as you move to the right, and that will look like this. And if the slope of a linear function is 0, the graph of the line will be horizontal, which of course will look like that. I mean, it's the blue one on that graph in case you are unsure. So calculating slope, you've probably seen how to do this before, but you might have forgotten. To calculate the slope of a linear function when you're not given it, you need at least 2 points or coordinate pairs. And remember, our coordinate pairs are written as, oops, is my pad not working? There it is. Sorry. Here, let's actually do that. They're written as x comma y. Or in function notation, you can think of it as x comma f of x, but generally students find this one to be a little bit more simple to use. So you can plug the points into the following formula to determine the slope. And that formula is m equals y2 minus y1 over x2 minus x1. And you should think of these as parentheses. In parentheses. It's kind of implied by the formula, but just in case you're confused, if you try to plug this into a calculator without the parentheses, you're going to get some really weird numbers. One of the important things to note is these subscripts. The numbers are really important. So the 2 needs to be further right on your graph than the 1. So like if you have a graph like this, and you're picking out 2 points to use, this point over here and this point over here, let's say those are the ones you're going to choose because they come out to even numbers and you don't want to use fractions or anything like that. Let's say it's like this. Make sure that this is your point number 2 and this is your point number 1. Point number 2 should always be further over to the right than point number 1. Otherwise, you're going to get your symbol backwards. You can always check the symbol based on the slope of the actual graph, but it's easiest to just make sure you're using the points correctly. So we're going to try it really quick with the points 0, 2, and 4, -6. So if we plug this in here, if we were to graph these, this is our x value, this is our y value, x value, y value. And since 4 is further to the right than 0, we know that this is going to be our x2, so this is going to be our y2, and this can be our x1, this can be our y1. So what we'd end up getting is -6 minus 2 over 0 minus 4. 4 minus 0. See, I just did what I said not to do. So then once we subtract those out, we get -8 on the top over 4, which is equal to -2. So this is going to be our slope right there. Okay, so calculating the y-intercept. The y-intercept of a linear function is the place at which the graph of the line crosses the y-axis. So if this is your graph, you've got a line that goes here like this. This point right here, that's your y-intercept. It is also the point where x equals 0, because obviously the y-axis exists when or where x is equal to 0. This tells us what the value of f of x is when x equals 0, which is especially important in real life problems. And we're going to look at an example later in this lecture, but that is something to keep in mind for what the value of knowing b is in a linear function. To calculate the y-intercept, you need to know the slope of a linear function and at least 1 point on its graph. That or you need to be given the y-intercept. And you can calculate the slope first and then plug in a point to calculate the y-intercept, which is usually what you're going to have to do. Let's practice using a line with a slope of m equals 3 and the point 4, 17. And when you're doing this, remember that 4 represents our x and 17 represents our y or our f of x. So this is 4 or f of x, whichever way you want to think about it. So we've got, in this case, we know that m equals 3. So if we were to write out our function as we know it right now, we'd get y or f of x, either one, equals 3x plus b. 3x plus b. Now in this case, we know that our y or f of x is equal to 17, equals 3 times our x, which is 4, plus b. We solve this out to get 12 equals 17 b, and then we subtract 12 from both sides and we get b equals 5. So that's how you can use the slope and 1 point on the graph to solve for your y-intercept. Okay. So identifying the slopes and the y-intercept. So this is just going to be a little bit of practice so that you can see how you actually tell what the slope and the y-intercept is in a linear function. So in this case, this one's pretty simple. It's f of x equals 2x plus 3. We know the slope is here. That's m. So slope is 2. And our b, our y-intercept, is just 3. So that is pretty easy right there. This next one is a little bit more difficult. We've got f of x equals 4. You can think of this as plus 0x. We don't actually have an x in our function, so 0 is our m. 0, and b is obviously going to be 4. So in this case, you have a horizontal line that just goes through the point, or the y value of 4. And then the last one, we've got f of x equals 8 minus 3/5 x. I just threw this one in here because sometimes people might get confused and go, well, m is always written to the left. And generally, if you're writing the equation out yourself, you should always put the x value for this left, but it's not necessary. So in this case, this is our b. So b equals 8. And then our n is actually equal to negative 3/5. So that negative sign needs to be carried over to our m, so minus 3/5. So hopefully that's not too tricky for you. It should be pretty easy to pick them out. The number in front of the x is always going to be your m, and the number on the other side is going to be your b. So let's talk more about that slope as a rate of change idea. So in this case, the rate of change, it's really helpful to look at a real life example. This is used all the time in physics. Rate equals change time, or distance equals rate times time. But for our real life example, let's do this. Let's say that a car starts 90 miles away from its destination. And for those of you that are following along, that 90 miles away means that it's negative because it is a distance away from where you want to be. So just keep that in mind for the future. It's traveling 20 miles per hour, so we want to know how many hours it will take to arrive. Now that 20 miles per hour, that's going to be our rate of change. So our rate of change, or our slope, is 20 miles per hour, right? Your car is moving. This is assuming that you're driving very constant speed, which of course is not true. And also if you're going 90 miles, hopefully you're on a highway. So you wouldn't only be going 20 miles per hour, but it works better with this problem if we keep the numbers kind of small. So if our rate of change is 20 miles an hour, we want to know when f of x equals 0, as f of x in this situation represents the distance from the car's destination. And in this case, 90 miles, which is our starting distance away. So when we've traveled 0 hours, our f of 0 equals negative 90. And that's because it's a distance away. It's not like we're not trying to go further away. We're trying to come closer. So our distance we think of as a negative value. So to finish this problem out, now that we know that our rate of change and our starting distance, we can write out our function. In this case, that function looks like this. F of x equals 20x minus 90. This 20 is our miles per hour. That's our slope. And this 90 is our starting distance. Right? And so when you look at the problem like this, you see that the y-intercept is important because that's where we start. That's why a b value is valuable in these real life problems. It's kind of like the location if there's nothing that has actually changed. And then our 20 miles an hour, in this case here, our m, that's the rate at which change actually occurs. So in this case, we plug in 0 for f of x and we solve. So we say 0 equals 20x minus 90, which we add 90 to both sides to get 90 equals 20x. Then we can divide both sides by 20, and x will equal 90 over 20, or 4.5 hours. And that's it for this lecture today. Tomorrow we're going to look at nonlinear equations and things like that. If you have any questions about this or anything like that, I'd be happy to answer them in class today. But you can go ahead and get started on assignment 5.